So hello everyone, welcome back to PC301 workshop, and we are ready with the third talk of the day. And for this we have with us Professor Meirav Zehavi from Ben Gurion University of Negev, and she'll be talking on parameterized approximation algorithms. So thank you so much for joining us, Meirav. Over to you now.
Thank you for inviting me, and thanks everyone for listening. So I will start with a few definitions. What are parameterized approximation algorithms? So towards that, first recall, then when we talk about polynomial time approximation algorithms, then we care about some approximation factor C. And then our objective is as follows. So given some instance I of the problem, we want to return a polynomial time solution such that its value will be at most c times the optimum for minimization. So we are at most c times worse than the optimum. And for maximization, we want the value of the solution that we return to be at least the optimum over c. So we are at least, we have at least optimum over c. Okay, and when we talk about parameterized approximation algorithms, then we still care about the approximation factor C, but we also have the parameter that we care about for the running time. So here specifically, we want the following. So I will first give a try, which is not exactly what we want, but then we will fix it. But we need this in order to understand the correct definition. So let's see this time. Here given an instance ik of our parameterized problem, then we want to run in FPT time, so f of k times polynomial into input size, and return a solution s such that, like before, for minimization, its value is at most c times opt, at most c times worse than the optimum, and for maximization, it is at least opt over c. Okay, so if k is a structural parameter, say the tree width of the input graph, then this definition is fine and it can be used as it is. But when k is the bound on the solution size, say we solve vertex cover and we seek a vertex cover of size at most k. So k is the bound of the solution size. So in these cases, this definition is problematic. Let's try to understand why. So suppose that k is an upper or lower bound on the solution size, then does it play any role in this definition? Does it really give us more power in terms of the running time? Let's see that it actually becomes irrelevant. For example, suppose that k is equal to 1. Then what actually are we trying to do here? So time f of k times polynomial in the input size is just polynomial in the input size. Right, it's f of 1. It's just this entire thing's become some polynomial in the input size, and yet k has no effect on the output that we want to have. Right, we still need to have a C approximate solution. So when we talk about decision problem, then k has a role. We want to find solution of size at most k or at least k. But here, this definition completely disregards this meaning, and k doesn't play any role at all. So this doesn't help us. The definition doesn't give us any more power than some normal polynomial time approximation algorithm. So we are going to change it a little bit. So there are several ways in which one can define parameterized approximation algorithms. Here I will give the following just because it is the easiest, I think, to understand. But for other purposes, the other definitions might be more suitable, for example, for kernels. But this you will see in other talks. So here the definition will be as follows. So only if we are given a yes instance, then we need to have an approximate solution with the approximation factor that we are looking for. So in any case, we want to run in time that is f of k times polynomial in the input size, but only if it is a yes instance, only if there is a solution of size at least or at most k. Only in this case, we have to return a solution whose size is at most c times k or at least k over c. Okay, so here you can see that k is important. If k was equal to 1, it's not that we need to find a C approximate solution to the problem. Right? K plays a role in this definition. So this is the definition we are going to work with in this talk and the next one. Okay, also please feel free to ask questions anytime in the chat, or you can turn on the microphone and ask questions. Okay, so I hope this definition is clear. So now let's move on. So I will directly give an example of a parameterized approximation algorithm. So in this talk, we will have two examples. The first will be easier than the second, and then if maybe we will have some time in the end, and I will show another thing. If not, then that is fine. So the first example that we will see, this is in some sense a classic example when you talk about parameterized approximation algorithms. It's for the partial vertex cover problem. So in this problem, we are given a graph G and the parameter K, and then we ask what is the maximum number of edges that can be covered by K vertices. So in particular, notice here that the parameter K is not bound on the solution size. We are looking for always a set of K vertices. So this is the number of vertices in the set, but what we want to optimize is the number of edges that these vertices touch, right? So K here is a structural parameter. So in this sense, we can already use the definition that we had in the first try. Okay, and what we will show here for the partial vertex cover is we will give parameterized approximation algorithm. Why do we care about parameterized approximation algorithm for this problem? So we could have tried to have just a parameterized algorithm. We could have tried to have to solve this problem in FPT time, or say we wanted to have a PTAS, a parameterized. We wanted to have a PTAS, and so first of all, trying to get running time FPT is unlikely to be possible because this problem is W1 hard with respect to K. So if we just want to have a running time that is not polynomial, just compensate on that, then this is not sufficient. We cannot solve it in FPT time. But also the other path is a dead end, because in polynomial time we cannot have a PTAS for this problem. Okay, we cannot solve it in polynomial time with approximation factor 1 plus epsilon for every epsilon, any fixed epsilon that we want. So both of these paths lead to the dead end, but we can combine both parameterized complexity and approximation and get the best of both worlds. So if we combine them, then we get FPT time and we get an approximation scheme. So let's see how we do this. So we will get a 1 plus epsilon like a PTAS, approximation factor. So we can solve it with approximation factor 1 plus epsilon for any fixed epsilon greater than 0. Oh, I see that there is a question. If not PTAS, what is the best approximation factor known for this problem? So I do not remember right now, but I think that there is a constant factor 2. Yes. So okay, so let's see how we get 1 plus epsilon approximate parameterized algorithm. So what do we mean by this? So when we are given an instance gk of the problem, so some undirected graph G and parameter k, the number of vertices in the set, we want to return a set of k vertices, some subset U of k vertices that covers at least opt over 1 plus epsilon edges in G. Okay, so this is what it means. It's a maximization problem. So 1 plus epsilon approximation factor means that we want to opt over 1 plus epsilon edges in the solution. Yes, so this problem doesn't have a PTAS. If you're asking what is the relation between problems that have PTAS, problems that are APX hard, and EPTAS, then this, if there will be time, I will talk at the end about the relation between these classes. Okay, this is an answer to a question in the chat.
Meirav, you go and I'll try to answer that question.
Okay. So the result we will see is by Daniel Marks. So So let's see what is the algorithm here. So let's denote by D this number. Why this number? This we will see later on in the analysis of the correctness of the approximation factor. So for now, this is some number that depends on K and epsilon. And let's order the vertices according to their degrees, from high degree to low degree. Okay, so recall, what is the objective of this problem? We want to cover as many edges as possible, right? We want to take K vertices and cover as many edges as we can. So at least intuitively, it seems like we want to pick vertices that have a highest degree, right? They will cover as many edges as we can. So there is question whether APX, I see that Sakit is answering this. Okay. Okay, so let's look at the two cases. So in the first case, the vertex that has the highest degree in the graph has degree that is at least D. It is at least larger than something. What is this threshold, D? Why we chose it like this, we will see soon. So when this vertex has such high degree, then actually we can just pick the first K vertices, and then we will be happy. We will have an approximate solution like we want. Notice that it is not correct that we can just pick the first K vertices always, because notice that indeed they have the highest degree, but we might be overcounting some edges. I mean, there are some edges that go in between the vertices that have the K highest degree. So maybe we want to pick some vertex that have a lower degree, but its edges are not overcounted, right? So it's not correct that we can just pick the K vertices of highest degree and get an optimal solution. But when the degree of the first vertex is so high, we can pick these K vertices and have an approximate solution with the approximation factor that we want. Because its degree is so high, then even though we are going to lose because we are overcounting some edges, I mean, when we take the sum of degrees, then this is not the number of edges that S covers, because some edges are counted from both sides. But because this degree is so high, then this overcounting will be compensated. So let's see this exactly in the computation. So notice that the value of S, the solution here that we picked, is at least the sum of the degrees of the vertices in this solution, minus K choose 2. Why K choose 2? Because this is the number of edges, this is an upper bound on the number of edges that we are overcounting. Right? In the worst case, when we look at these vertices in S, then they have all of the possible edges in between them, and all of these edges are counted twice. So actually the value of the solution S is the sum of the degree minus the number of these edges, because each one of them is counted twice. So we need to reduce that from our count. And the value of the optimum, notice that it is at most the sum of the degrees of these vertices. I mean, what is the largest number of edges that K vertices can count? It is at most the sum of the degrees of the K vertices with highest degree. Right? This is the best case that can happen. So we have this lower bound on the solution, on the value of the solution that we have, and we have this upper bound on the value of the optimum. So let's see that together. This means that we have the approximation factor that we want. So let's look at this. So we want to say that the value of S divided by the value of the optimum is at least 1 over 1 plus epsilon. Right, because if this holds, I hope that you can also see my pointer when I'm talking. So because if this holds, then notice that it means that the value of S is greater or equal than opt divided by 1 plus epsilon. This is exactly what we wanted, what we want to show. So let's see that this holds. So instead of value of S, we write here at the top the lower bound. And instead of opt, we write here at the bottom the upper bound on opt. And now notice that when you look at this, then you have this sum and this sum here below, it's the same. So it becomes 1 minus K choose 2 divided by the sum at the bottom. But notice that the sum at the bottom is at least the degree of V1. So in particular, the sum of the bottom, at the bottom, the sum of the degrees is at least D. And this is why we have here the choice of D as it is, because now when you will substitute D, you will get here 1 minus epsilon over 2. You see the k choose 2 here gets cancelled, and here you have left with epsilon over 2. Okay, so the D was chosen to be large enough so that we will have this equality. And you can see that for any fixed epsilon greater than 0, 1 minus epsilon over 2 is at least 1 over 1 plus epsilon. This is just some calculation. Overall, you get that the value of S so it is indeed 1 plus epsilon approximate solution. Okay, so this is the first case. So when the degree of the first vertex is so large, we can just pick the k vertices of high degree. The loss there gets compensated by the so large degree of the first vertex. So now let's look at the second case. So in the second case, we are now the degree of the first vertex is not that large. It is at most d. But now notice that this case is also very good for us because in this case, even the highest degree vertex doesn't have that large degree. So the entire graph actually has a degree that is bounded by some function of k and epsilon by d. So this should remind you some method that you saw that you should know, some basic method in parameterized algorithm. Okay, so we are happy when the maximum degree is at most d, because then we can solve the problem optimally by this method. So what is this method? This is what is called randomized separation, or coloring with two colors. So how can we solve the problem when the degree is bounded? So in this case, we can color the graph in two colors. So we do a lot of coloring iterations. And the objective is that at least one of these coloring iterations will be such that, so this I'm going through a bit fast because I'm assuming that audience knows the method of randomized separation, but if something is not clear, please ask. So the goal here is that the solution, the set of k vertices that we seek as a solution will be colored red, and that all of the neighbors of the vertices in the solution will be colored blue. And that is okay, because the number of vertices whose color is important to us is just a function of k and epsilon, right? This red part is just k vertices, and this blue part, all of the neighbors of the solution, this is at most k times d vertices, because each one of the red vertices has just at most d neighbors. So overall, the entire neighborhood is of size at most k times d. So this means that one can use randomized separation by generating this many kd plus k choose k, many coloring function. Either you randomly color the graph each time, or you use the randomization tool. And it is guaranteed that you can perform only this many coloring iterations to guarantee that in at least one of them, the solution will be red and the neighborhood will be blue. And finding a colorful solution, this is an easy task that can be done in a polynomial time. Seeking whether there is the red solution so that all of its neighborhood is blue, and that is doable in a polynomial time. Okay, so in the case 2, we are also happy because the degree is bounded, and then one can use the standard method in parameterized complexity. So notice that in this case, we actually solved the problem optimally. Okay, in the first case, we solved the problem in polynomial time, but we didn't solve it optimally. And in the second case, we solve it optimally, but now it's in FPT time. So overall, it is an FPT approximation scheme. Okay, good. So now let's go to the more complicated example. Okay, so now we will talk about the K-path transversal problem. So here we are given an undirected graph G and the parameter K, and we ask what is the minimum size of a set of vertices such that in G minus S we have no path on k vertices or at least k vertices. It is the same question. Okay, so we wanted to remove fewest vertices as possible, such that we hit all of the paths on k vertices. Here I mean simple paths. So it's like a hitting problem. We want to hit all paths on k vertices. And notice again that here the k is the parameter is not the solution size, right? What we want to minimize, we want to minimize the size of the set S, number of vertices that we remove. And k is the size of the paths that we want to hit. Okay, so again, it is like a structural parameter. Okay, good. So for this problem, we need a FPT, because even if you want to check whether there is a k-path, this is NP-hard. So even if you want to check whether the solution size is 0, which means that you need to know whether the graph already doesn't have any path on k vertices, or whether it still has, and then the solution size is at least 1. So just checking if the solution size is 0, this is already NP-hard because it is just equivalent to the k-path problem, right? Checking whether a given graph has a path on k vertices. So this is already NP-hard. So FPT time, so we need FPT time for this. Approximation will not help us, because if you have some C approximation, then what is the meaning of C times 0? Right? We need to, the case for the solution size is 0. We would need to handle in polynomial time. And this we cannot do, so we need the FPT time. We need FPT time already for the case where the solution size is 0. And we also need approximation. We cannot solve this problem in FPT time. Why? Because notice that when the size of the parameter k is a constant, then already the problem is NP-hard. So the problem is para-NP-hard. Why is this? So suppose that k is equal to 2, then what does it mean that we want to hit all of the paths of size 2? What is this problem? So this is a problem that all of you know. What is the meaning of hitting paths of size 2? This is exactly like hitting edges, right? So we want to find the minimum size solution such that it hits all edges, eliminates all edges. So this is exactly vertex cover. So already when k is equal to 2, we get an NP-hard problem. So we need also approximation. We cannot have an FPT algorithm for this, because when the parameter is constant already, it's NP-hard. So we need both FPT and approximation. Okay. So what we will see here, it is a result by Lee. So we will see an order log k approximate parameterized algorithm. Whether you can get this approximation in polynomial time, we don't know. So for hitting set, which is a more general problem than this one, in some sense, then this is unlikely. But for this problem, hitting k-paths, we don't know. But in any case, this is the approximation factor that we will see here. So an order log k approximation factor in FPT time. So what does it mean? It means that given an instance of the problem, gk, we want to return a set of vertices S of size at most order opt log k. So you can see it's a log k approximation, order log k approximation, such that it is a solution, which means that in G minus S, there is no path on k vertices. Okay, so we return a solution that is, in terms of its size, it's order log k approximation. Okay, so let's see how we do this. Okay, so the running time that we will see is this running time. It was improved since then. There was a later paper that improves upon this. So we will give an algorithm that solves this problem with approximation factor order of log k, and in this running time. How we get this running time, you will see from the calculations immediately. Okay. So let's try to have another view of what we are trying to achieve. So in the beginning, it will look like a strange view, but you will soon understand why it actually makes our life easier. So what actually do we want to get? We want to get a set of size at most order log k opt, such that when we remove it, then we don't have any kpf in the graph. So in another way, we can think about it like we are trying to find some set of size order log k times opt, such that when we remove it, in each one of the connected components that we have, there is no path on k vertices, but this is the same. And in other words, it is like we want to remove some set of this size, such that in each one of the connected components that we get, the solution size will be 0. This is okay. I mean, we want to not have a kpf in the remaining graph. So in particular, we don't want to have a kpf in each one of the connected components, which means that the solution size in each one of them should be 0. Okay. Okay, so let's look at a slightly seemingly easier task, which is the following. So now instead of trying to get some set of vertices, such that after we remove it, the solution size in each one of the connected components that is left is 0, let's try just to find the set of this size, of size the order log k times the optimum, such that when we remove it in each one of the connected components, the solution size, the optimal solution size, will be some function of k. So this is easier. I mean, we just want to have now components with small solutions. Okay, rather than having to solve the problem, to have components with solution size 0. So why do we care about this easier task? Is it really easier? So this is what we are going to show now, that if we are able to get to this situation, if we are able to find a set of size at most order log k times opt, such that in each one of the connected components, the solution size is f of k, then I will show you now how we can be done. And then in the rest of the talk, we can focus on finding this set of size order log k opt, such that it doesn't solve the problem, but just says that in each one of the connected components, the solution is small. Okay, so let's see why, if we get to this situation, we are done. So let's see why this easier task is sufficient. So suppose let S be some set of size order log k times opt, so some c log k times opt, such that in each one of the connected components that we get after we remove it, the size of the solution is some function of k. So here taking k cube will work. Okay, so suppose we are able to reach to solve this problem that corresponds to the easier task. And let's see why this means that we are done, why this is sufficient. Okay, so now we will look at each one of the connected components in G minus S. We know that in each one of these connected components, the solution size is at most k to the power of 3. This is what we said that we achieved so far. And now let's see how it means that we can solve each one of these connected components optimally. Notice that here we have a lot more power, right? The problem before was that k was unrelated to the solution size. It was just the size of the path that we wanted to hit. Now, when we focus on such a connected components, then yes, k is still the size of the path that we want to hit, but it's also related to the solution size. So we can use techniques that are related to this, that in particular are FPT by the solution size, because now it's okay. Now the solution size depends on k. So how do we solve this? How do we find the solution of when we know its size is at most k to the power of 3? So we will get this running time, k to the order of the f of k, which is the bound on the solution size in each one of connected components. So we are going to use a very basic method in parameterized algorithm. We are going to use branching. Okay, so as long as we still don't have a solution, okay, we are looking now at one connected component whose solution size is at most f of k. So as long as we still don't have a solution, there is still a k-path there, then we find such a k-path as a simple path on k vertices. This we can do using known algorithms. There are no known algorithms for the k-path problem, for finding a path on k vertices to work in time single exponential, in 2 to the order k time polynomial in the input size. So we find such a path, and then we need to hit it. So every solution will pick at least one vertex from this path in order to hit it. So we bunch on all the possibilities. Do we take the first vertex, the second vertex, the third vertex, and so on? So we try every possibility, and then we get k branches. To the degree of the search tree is k. And then again, in each one of these branches, we ask, is there still a k-path in the connected component? And if the answer is yes, then again we find a k-path. And again we branch on which vertex of this k-path we are going to take. So notice that we get here a bounded search tree, such that first of all, the degree the degree of every node here is k. We have k branches. We have exactly k branches. And moreover, each time we pick some vertex to our solution, we add another vertex to our solution. And we know that the optimum here is at most k to the power of 3, or f of k. So this means that after doing this f of k times, so the depth of this search tree should be f of k. After f of k times, we already exhausted all of our branches. So if we didn't find the solution then we should go and look at the other branches. Okay, so this is just a search tree with degree k and depth f of k. And therefore, this is the running time we get. Right, because every time the size of this tree, when we look at the size of this tree, every time we have k children, and the depth is the f of k, so it's k times k times k, f of k times. This is the size of this tree, and overall this is the time that we get. Okay, because the time we spend in its node is just 2 to the order k times polynomial in the input size. So overall the size of the tree is here the dominant factor. So this is exactly the running time that we promised before. So you can see in particular that when the solution size is bounded by some f of k, here we took k to the power of 3, then we are already done. We can solve the problem then optimally in each connected component. Let's see this more precisely. So what happens? So in the beginning, we got some approximate, it is not an exactly approximate solution, it's approximate solution for our easier task. So it's an approximate solution. It's a set of size order log k times opt, such that when we remove it, each connected component has solution of size at most f of k. So we first take this set. So this is this term here. And then afterwards, to get a solution to our problem, we look at every connected component C and solve it optimally. So we also pay for every connected component C, opt C. So opt C here is the optimum for the connected component C. So this is overall what we pay. So this is at most, so here we write this term again. And what is the sum of the over opt C? So this is at most opt, right? This is at most the optimum. If we want to every optimum solution that hits all paths of size k, in particular, it has its part that hits all vertices of size k in the first component, and it has some part that hits all the k paths on the second components, and so on. And here we solved optimally each one of these connected components individually. So in particular, if we take all of these optimal solutions that we have, each one of them is upper bounded by the part of opt in the corresponding component. So overall, their sum is at most opt. So anyway, I mean, this term is very small compared to the set S that we have from the first place. So we get here that the size of the solution that we return, the set S plus all of these optimal solutions for the connected components, this is at most order log k times opt. There is the size of the components play no role. No, we don't care about the size of the components here at all. We just care about that the solution size in each one of them will be small. because essentially what we have here for each component is an FPT algorithm, exact FPT algorithm, parameterized by k plus the solution size. And the solution size here is at most f of k. Okay, so notice that this is also where the strange running time that I mentioned in the beginning comes from, because k to the power of f of k, this is k to the power of 3, because f of k we choose to be k to the power of 3, why k to the power of 3? So we will see this in the next part. I mean, now we will try to find this set S of size at most order log k times opt, such that in its connected component, the solution size is at most k to the power of 3. Okay, so from now on, we can forget about the fact that we are trying to solve k-path transversal. We now care about just solving getting a solution for the easier task. So what it means? It means that we want to find a set of size order log k times opt, so that when you remove it in each connected component, the solution size is at most f of k, which for our case would be k to the power of 3. Okay, good. So how we are going to do this? So we are going to look for some set R. We are going to think about the vertices in this set as red vertices. So we are trying to find some solution of red vertices. It is a solution because what we want to find is a solution. We want to find some set R such that when we remove it from the graph, we no longer have any path on k vertices. And we want the size of R to be at most k times opt. So if you still remember, like this is not a solution, a good solution for the problem we started with, because yes, it is a solution, meaning that it hits all the paths on k vertices. But here from the set R, we only require it to be of size k times opt. So this is not an order log k approximate solution. And so we will like to find such a set R. So this is much easier than this. You can do either greedily or using ILPs. I will show soon. So we want to find some set R such that its size is at most k times opt, and it is a solution. It hits all the k paths. And we also want to have another property. We want to have the property so that there exists some set S of vertices, such that the size of S is at most order of the size of R over K, and every connected component in G minus S has at most K to the power of 3 vertices from R. So in fact, we will show that for any set R of at most K opt vertices that hits all K paths, the second property is true. Okay, sorry. So we will show that whenever you find a set R that satisfies the first condition, then necessarily the second condition is satisfied. Notice that the second condition here is existential. We want to say that there exists some set S such that this is its size is small, and when you remove it, then every connected component has at most K to the power of 3 vertices from R. Let's try to understand what is the meaning of this set S. How does it help us in achieving our goal? Our goal was to find a set of size at most order log k times opt, such that when we remove it, every connected component has solution size at most k to the power of 3. How is this related to what properties we want from this set S? So the fact that we demanded that this set S will have size at most order R over K means that this set S would have size order opt, right? Because R is at most of size K times opt, so R over K is at most order opt. And what does the second condition means? It means if every connected component of G minus S has at most K to the power of 3 vertices from R, it means that every connected component of G minus S as solution size at most k to the power of 3. Right? Because the optimal, remember that R is a solution for the problem. R hits all of the paths of size k. So if you look at some connected component, and there you have at most k to the power of 3 vertices from R. So the optimal solution for that connected component, it can only be of the same size, meaning k to the power of 3 or even smaller, right? Because the restriction of R to this connected component is in particular a solution. So the optimal can only be the same or better. Okay, so overall, what the second condition means is that there exists a solution for our task. This is existential. We will soon talk about what it means computationally for us. But the second condition just says that there exists a solution for our task. There in the following, that its size is at most order opt, and what does it mean that it is a solution to our task? It means that when you remove it, every connected component has a solution size at most k to the power of 3. So the easier task, the problem that we are trying to solve now, assuming that we can get this set R, it has a solution of size order opt. Okay? So how can we use this second property in order to solve our problem? So let's see this. So we would like to get a set S prime of size at most order log k times the size of this set S, which we don't know. This is just existential, and then our task will be done. Right? Then we get a solution of the size that we want, log k approximation, and it will have the property that every connected component has solution size at most k to the power of 3. So how do we get this set S prime? So for this, we are going to use a known black box. Okay, so suppose somehow we get this set R. How we get this, we will soon discuss. So suppose somehow we get this set R, and suppose that we prove that the second property is correct. This we also need to prove this existential claim about the existence of this set of size order opt that partitions R. Then how do we solve our task? So for this, we are going to use a black box, an algorithm for the following partition problem. So this problem is defined as follows. So it's in its input, we are given an undirected graph G, and we are given some set of red vertices, and we are given an integer k prime, and we want to find the set of minimum size such that in each connected component of G minus S, we have at most k prime vertices of R. Right. So what we know because of the existential claim, the second property, that we know that if we look at our instance with G R that we found and k prime that is equal to k to the power of 3, then we know that this instance has a solution of size order opt. This is exactly what the second property says. Okay, so it says there exists a solution of size order opt for this problem. When we look at this in the situation that we arrived. Okay, so this problem, it has an order log k approximation algorithm that runs in single exponential time. It uses some method in the approximation algorithms. So here, I mean, for us, we use the parameter is actually this k prime, which means k to the power of 3. So we get an order log k approximation algorithm that runs in time 2 to the order of k prime, which is k to the power of 3. This is still within the running time that we want. And this will give us this set S prime that we were looking for. Okay, so we can use this black box and get the solution that we want. So let me just return for another moment to the previous slide, so we will make sure that we understand this. So what is our task now? Our task now is to find this set R that hits all k paths, and its size is at most k times opt. And we will also need to prove an existential claim that there exists a solution not a solution to our easier task. There exists some set of size order opt such that it partitions R. In every connected component, there will be at most k to the power of 3 vertices from R. If we do this, then we are done, because by using the black box that we just said, the black box for this separation problem, it will give us an order log k approximate solution for this separation problem, which means it will give us a solution of size order log k times opt, order log k times s, at most order log k times s, such that in each connected component, there are at most k to the power of 3 vertices from R. So we solve the easier task. Okay? This is fine. So now the next step that we want to do is to find this set R and prove the existential claim. So this is the things we are left with. If we do this, then we are done, because we get the easier task by these black blocks, and we already said that the easier task is sufficient. Okay, so let's now go on to understanding how we can find this set R. Good. So the set R actually can be found using just a greedy algorithm in the following sense. You seek if is there still a k-path in the graph. This we can do using a known algorithm that works in time 2 to the order k times polynomial in the input size. And if there is still a k-path in the graph, we take all of its vertices. And then again, if there is still a k-path in the graph, we take all of its vertices, and again and again. So this is actually a simple greedy algorithm for this, and like it's an FPT that works in FPT time, because we need to understand if there is a k-path in the graph or not, and it is k approximation, because you take k vertices, you take all of the vertices in the k-path, but any optimal solution will have to take at least one vertex from this set of size k that you took, right? Because it needs to hit this k-path. So you get here this ratio that you want. So it's a k approximate solution. But in the paper itself, there is a more complicated thing, which I still want to show here, because I think this is very interesting. So here specifically, you can use the greedy algorithm that I just explained in order to find a solution R of size at most order opt times k. So it is a solution that hits all k-paths. So here, let me show you a different way to do this, because this way might be useful for other things when the greedy approach doesn't work. So for this, we are going to write a linear program. So we have here a variable xv for every vertex v. And what we want to do is we want to hit all of paths on k vertices. So here we have this constraint for every path. This exactly means, notice that when we take the sum of the variables corresponding to the vertices in this path, so this sum should be at least 1, which means that we hit all of the we hit this k path. Okay, if it was if we added the constraints that every variable should take 0 and 1, then this would be exactly the k-path transversal problem. Okay, but here we are looking at the relaxation. Okay, this is okay. This is the program for a k-path transversal. Okay, all the variables are non-negative. So what we would like to do is to solve this linear program. So how can we solve it? So let me say this immediately. We would like to solve it so that after we get some solution, some assignment to the variables that satisfies all of the constraints and minimizes these objective functions. So when we get some solution, we will define R just to be all of the vertices that got value xv at least 1 over k. Okay, if you define R like this, then notice 2 things. So notice that G minus R doesn't have any k-path, because for any k-path that you are going to look at, any path on k vertices, this constraint was satisfied. And in order for this constraint to be satisfied, at least one of the variables that correspond to this path must take value at least 1 over k. right? If each one of them took a value that is smaller than 1 over k, then overall their sum won't be at least 1. So we are, if we take all the vertices that got value at least 1 over k, then we hit all of the k paths. And also, what is the size of this set R? So notice that the size of set R is at most k times frac, the value of the solution to this LP that we got, an optimal fractional solution to this LP. Why is it at most k times frac? Because we rounded up only variables that got value 1 over k. So we are paying at the worst k times more the optimum, the frac. And the optimal value of this linear program is at most opt. So frac is at most opt, and therefore this way we also get a solution of a size at most k times opt. And just one thing that I didn't say is how do we solve this linear program? So you can look that you can see that there is an exponential number of constraints here. For every k path we have a constraint. So we cannot even write this program explicitly, but this is fine because in order to solve a linear program, what we need is a separation oracle. And what that means is that if I give you a solution to this linear potential solution, okay, if I give you some assignment as a potential solution for this linear program, then you need to tell me if it is really a solution, yes or no. And if no, if it is not a solution, then you need to give me some constraint that is not satisfied. Okay, so, and this we can do. So this is also why I wanted to show this approach, because this is an interesting way to solve, it gives us an interesting way to solve in FPT time a linear program with a huge number of constraints. So you look at the separation oracle, and now it will be a separation oracle that works in FPT time. This is what is nice here. So there is the question, but the number of constraints is large, right? Yes, it is large, but all we need is a separation oracle. And then you can use the known method, like the ellipsoid algorithm that will solve it. So how do we do the, how do we, yeah, I didn't explain it yet. I will now explain how we have this separation oracle. So if I give you some solution, a potential solution, some assignment, how can you verify whether it is a solution or not? So how do you verify whether there is a constraint here that is not satisfied? You need to check whether there is a path such that the sum of its variables is smaller than 1, right? Then you have a constraint that is not satisfied and you can return it. So how can you do this? You look at your graph and you think about it like a weighted graph. So the weight of a vertex will be the value of its variable. And then what are you actually asking? Is there a path on k vertices whose weight is at most is smaller than 1? This is weighted k path, and for this you can use the known algorithm, right? So trying to find here whether a constraint is not, whether there is a constraint that is not satisfied by a given assignment, it is the same as solving weighted k path. That is fine. So this is quite nice. I mean, maybe it's not that useful because we can use here a greedy algorithm, but still it tells you how given a linear program that seems not clear how to get a separation oracle for it, then here FPT is very helpful because you can get a separation oracle that works in FPT time. So this is like an independent idea that might be useful some other places when you design parameterized approximation algorithms. Okay, so we already gave two approaches, how to find the set R, which is a k-approximate solution. Okay, it hits all of the k paths and it sizes at most k times opt. So now we still need to prove the existential claim. We still need to prove that there exists some set. We don't need to say how we find it. This we already discussed earlier, that we use a black box to get some order log k approximation. All we need to now say that there exists some set S of size at most order R over K, such that when you remove it, every connected component of a G minus S has at most K to the power of 3 vertices from R. Okay, so we want now to say an existential claim. There exists some S that satisfies these two properties. Its size is small, R over K, and it separates R. Okay, so this is what we are going to do now. So how we are going to prove it? So let me just say that here I wrote it like this, so it will be simpler, but actually the S that we just need S to be of size at most opt, where opt is the optimum for the K-path transversal problem, plus order R over K. This is essentially the same as right in here, but not exactly, because the R, maybe by luck, you got a very good R, and then R over K is even much better than opt. And like you got R that is of size, I don't know, log K times opt. So we still allow here in S to put opt. Okay. So this was just a side comment so that everything will be exact, but okay, so how are we going to construct this set S? This is just, remember, this we don't need to do efficiently. We just need to show that there exists S with these two properties. So first we are going to insert to this set S an optimal solution to the K-path transversal problem. So this costs us opt, that is fine. This is good. And now we are going to add some things to this set S star. So what we want to add some things whose total size will be at most R over K, order of R over K, such that in each connected component there will be at most K to the power of 3 vertices from R. Okay, this is our goal. We need to show that there exists a set with this property. So as long as this property is not satisfied, as long as, I mean, S star initially is an optimal solution for K-path transversal, but we are adding for it stuff. So as long as G minus S star doesn't have the property that we want, I mean, it has some connected components with more than K to the power of 3 vertices from R, we do the following. So we take some longest path P in C, in this connected component, this problematic connected component, and we add it to S star. Okay, so this is what we do. This is how we construct the set. This set doesn't matter efficiency. This is just existential. So this is how we construct it. So notice that first, it is trivial to see that one of the two properties that we want is satisfied. I mean, when you take eventually this set S star, after you ended running this procedure, then obviously in every connected component, there is at most K to the power of 3 many red vertices, right? Because as long as we had some connected component that has more than K to the power of 3 vertices from R, we continued and added more and more and more vertices. So when this is done, we have this property. Every connected component has at most K to the power of 3 many red vertices. But okay, so we did this. But why didn't we add too many vertices along the way? We need to ensure that the number of vertices that we added while taking care of all of these problematic connected components, we need to make sure that this is at most order of the size of R over K. So this is what we are going to prove now, okay? That we didn't add too many vertices. Okay, why is the size of S star eventually at most order R plus over K? Plus opt. I mean, eventually, in the beginning, we added an optimal solution. So for this, we are going to do a charging argument. So whenever you add the vertices of some long path in a connected component to S star, we charge the cost of adding them. What is the cost? We added the number of vertices in this path. This is the number of vertices in this path. We charge their cost to all of the vertices to all of the red vertices in C uniformly. What does it mean? So notice that P has at most, it even has less than K vertices. Whenever you look at the connected component and the longest path in it, it has size strictly smaller than K, because in the beginning, we already added the solution to the K-path transversal problem. So all the paths of size at least K are already hit. So whenever we take a longest path here, then it has less than K vertices. And we know that there are at least, there are even more than K to the power of 3 vertices in the connected component. So each one of them, each red vertex, what is the charge that it gets? At most 1 over K to the power of 2, right? Because we charge K to at least K to the power of 3 vertices. So each one of them gets charged at most 1 over k to the power of 2. So what we would like to show, so it will take me another 2-3 minutes to finish. So what we want to show is that every red vertex is charged at most k times. Why would this be helpful for us if we can show this? Because then notice that what is the charge that every red vertex gets? Every red vertex will get charged at most 1 over k, right? Because in every time it gets charged at most 1 over k squared. And if we can prove that the number of times that we remove this long path and charge the same vertex is at most k, then the charge that every red vertex gets is at most 1 over k. So what is the total charge that we pay? So if every red vertex got a charge 1 over k. So in total, what is the charge that we pay? The size of R over k. This is the total charge, right? We sum over all of the red vertices. And this total charge is exactly the number of vertices that we added. Right? Every time we add x vertices, and we take this x and we put it as a charge to the red vertices. Right? We took some v of p, many vertices, and this number we now consider it as charge. And we assign this charge somehow to the red vertices. And then eventually we look what is the charge that we got overall. And we can see that this is the size of R over k. So this is the number of vertices that we added. So we already said that every time that we do this charging operation, every red vertex gets a charge that is at most 1 over k squared. So now it remains to show that the number of times that a single red vertex can be charged is at most k. So let's see this. Why every red vertex? At most k times it will be involved in this in a bad connected component. So let's see this now. Okay. So there is the following observation, that when this is some independent observation that we are going to use about the graphs. So if you look at some graph, connected graph, like a connected component in our case, and you look at some path P which is longest there, then if you remove all of the vertices from P, then the size of the longest path in what remains drops. So it is like you can think about it in the following way. If you look at some graph and you take some longest path in it, and you take all of its vertices, it is the same as if you have, it is like saying that you have hit all of the longest paths in this graph. And then so it means after you remove this vertices, the size of longest path is less, at least 1 less than it was before. So let's say intuitively see, at least in the picture, why it would hold. So suppose it was false. So you have here some longest path, and it doesn't hit all of the longest paths in the graph. So there is some disjoint longest path from it. So you have 2 longest paths. But then because it is connected, there is some way to reach one longest path from the other. And whatever way you will think about, it will help you construct a path whose size is longer. And this is contradiction that now we are looking at 2 longest paths. For example, if you could have reached one from the other by a path that looks like this, then here you have a longest path, longer than before, 6 vertices compared to 5. If it was like this, then here you have a longer path. So this is just some picture to convince you that this observation is correct. So what does it mean for us? Whenever you take a longest path and you remove its vertices, the size of the longest path becomes smaller. So how many times can we look at the component and take a longest path? At most k. We start with the path of the longest path in the beginning has size at most k minus 1. Because we know we don't have paths of size at least k after in the beginning, after the initialization. So we have some connected component of longest path has size at most k minus 1. We take a longest path here. Now it is possibly split to different connected components, but in each one of them, the size of the longest path is at most k minus 2 now. And now, once we will look at each one of them, that is each one of them that is still bad. It still has too many red vertices, more than k to the power of 3. We again take a longest path, but here the size of the longest path in the next step in each one of the resulting connected components will be smaller. So overall, this process can be done at most k times. After that, we will get an edgeless graph. So let's look, let's try to trace some red vertex and see what happens. So if we look at this red vertex, how many times is it charged? It is charged here, then it goes to some connected component. After we remove the longest path, it is in some connected component left. Maybe then again we take a longest path, then okay, we charge it again. But the number of times that we can charge it is at most the depth of this tree, which is k. So indeed, every connected component is charged at most k times, and this completes our proof. Okay, so overall, this completes the existential proof, and using the previous components that we have, we overall got here an order log k approximation algorithm in FPT time for the k-path transversal problem. Okay, so I will end the lecture here. Please feel free to ask questions.
Thank you so much, Meirav. Thanks for the talk.